In the last video, we explored the Thevenin and Norton equivalent circuits, which takes any arbitrarily large and complex circuit and reduces it into a single voltage source in series with a resistor or impedance in the case of a Thevenin, or a single current source in parallel with an impedance or resistance in the case of a Norton. That technique involves two steps. First, in the case of a Thevenin, which is what I'll primarily be talking about, we find the open circuit voltage, and that's what we define as the Thevenin equivalent voltage, and then we find the equivalent resistance between A and B. In finding the equivalent resistance, we always turn off the sources, the independent sources first. Note that I made the mention that if there are dependent sources in the problem, we must keep them active in the circuit, but we need a different technique. This different technique for finding the equivalent resistance is called the source driving technique. The source driving technique works for any circuit with dependent or independent sources in it, but it's required when there are any dependent sources. So this is a technique that you must become familiar with because there are situations where you will have to use this technique in order to solve the problem. There's no getting around it. The procedure for finding the equivalent resistance between any two nodes using the source driving technique is as follows. First, we start by setting all independent sources to 0 volts or 0 amps. It's the same thing for when we can just use resistor reduction. But then, given that we could have dependent sources in there and we need to understand how they're affecting the equivalent resistance, what we do is we connect an independent source, voltage or current, to the output terminals. For simplicity of the mathematics, we're going to typically choose the voltage source, we'll call V sub SD, to be 1 volt, and the current source, if we choose so, to be 1 amp. That just because it makes the math easy. And note that we can scale these because these are linear circuits and we'll still get the same functional relationship. Then if we're applying a voltage source to the output, we're going to solve for the current drawn from that voltage source. If we apply a current source to the output, we're going to solve for the voltage dropped across that current source. In either case, the equivalent resistance is then going to be given as the voltage divided by the current. So, for example, we're noting that we have a circuit that can be modeled with an equivalent resistance, right? So we have a resistive circuit, and pretend we don't know what's inside that circuit. All we have access to are nodes A and B. So what we're going to do is we're going to attach an independent source to the output. In this case, I'll choose a voltage source. I'll call that VSD equals 1 volt. Note that since I'm assuming the circuit's resistive, I'm going to see a current being drawn from that voltage source, ISD, that is going to obey Ohm's law. So the equivalent resistance is just simply going to obey Ohm's law and be VSD over ISD. In this case, 1 over ISD. Okay, so let's do an example. We're going to find the equivalent resistance seen between A and B in the following circuit. Note that this circuit could be solved using the same techniques that we've been using in the past. So what I would like you to do is to solve it using the source driving technique and then solve it just using resistor reduction to ensure that you get the same solution. So the first thing what we're going to do is redraw the circuit, turning off all independent sources. Okay, so here's our equivalent circuit. There's only 3 resistors. This can be reduced pretty quickly just using standard resistor reduction, noting that we have 35 in series with 15, making 50. That's in parallel with this 50. So we know actually, just by inspection really, that the equivalent resistance is going to be 25 ohms. But let's use source driving technique. What we're going to do is attach an independent source to the load. I'm going to make this a current source of value 1 amp. And my objective is going to be to find the voltage dropped across that current source, V sub SD. Note the polarity that I assigned, the positive on the top, negative on the bottom with the current going up, and that's because this is the only independent source I have in the problem. This must be supplying power. So I just know that that's the case. Okay, so in this problem, I've got one essential node. So I'll use nodal analysis to solve this, or two essential nodes rather, but one where I'll be writing an equation. So I'll choose my ground at the bottom, therefore making V sub SD the node on the top. KCL at VSD is going to be VSD minus 0 over 50 for this path. Same term for the one in the middle, VSD over 50, and that must equal 1 amp. Therefore, V sub SD is going to be 25 volts. Finally, the equivalent resistance is going to be given as VSD over ISD, which is 25 volts over 1 amp, which equals 25 ohms. Again, just recall that just by using equivalent resistance, we could have found that by inspection immediately by saying 35 plus 15 in parallel with 50. So we see that this method works the way we anticipated it to work. The powerful thing about this method, though, is that this technique works even with the dependent sources being present in the problem, where resistor combinations cannot work if there are any kinds of active elements present. Okay, let's do another example with some dependent sources in the problem. We're going to find the Thevenin equivalent resistance seen between terminals A and B. So note that we're only finding the Thevenin equivalent resistance in this problem. I could ask you to find the full Thevenin equivalent circuit, of which you need to find the open circuit voltage first. Source driving technique is only used for finding the resistance. So we need to first redraw the circuit, turning off independent sources. Okay, we only had one independent source, and that was the 5-volt voltage source, so that becomes a short circuit, and keeping the two dependent sources of the problem. So again, we're going to attach an independent source on the output. I usually like to use current sources just because the voltage that I find being dropped across that current source is going to also be the same as the value of the Thevenin equivalent resistance, because it will be V over 1. Okay, so noting here that our value V, which is on a dependent variable, just equals V sub SD directly because they're in parallel with one another. Okay, so what are we looking at for the analysis? Well, we've got two essential nodes, so we can do this in one KCL equation, and we would require 1, 2, 3 meshes, although 2 of them are known, so we could do this in one mesh equation as well. I'm going to choose nodal analysis. So this top node becomes V sub SD. Okay, so KCL at VSD will be 20I plus VSD over 25, it's current through the 25 ohm resistor, and that must equal 1. We have a dependent variable I in the problem, so we need a constraint equation. I, in terms of nodal voltages, would be 0 minus the nodal voltage at this point, which is 3 times V, which equals 3 VSD. So I equals negative 3 VSD over 2K. Two equations, two unknowns. We can solve this problem, and we get that VSD equals 100 volts. Therefore, the Thevenin equivalent resistance, which is VSD over ISD, equals 100 volts over 1 amp, or 100 ohms. So this circuit, according to A and B, behaves like a 100 ohm resistor.